Welcome to EE252 Electronic Devices and Circuits lecture. Today we are going to talk about BJT H parameter model. We already talked about the small signal model in the previous lecture. We said the BJT can behave like an active linear two-port device under certain conditions. So those conditions were the input signal has to be small. In other words, VBE should be less than about 10 millivolts, preferably even smaller, and the frequency of the signal has to be very small in the kilohertz range, not in hundreds of kilohertz or megahertz range. And also, the another assumption was that it is properly biased so that the transistor will not operate in the saturation or cutoff region. So under these assumptions, it was possible to convert this BJT into a linear active two-port device. But we need to remember one thing. In this small signal model, right, which behaves like a linear active two-port device, we do not use it to find the operating point or the Q point. We can only find the small signal model assuming that it is properly biased. If it is not properly biased, then of course these things will not work. So if it is properly biased, then we can use it for finding small signal parameters. And also we need to ensure that the signal change is small so that around the Q point, both in input characteristic and the output characteristic, the changes are only very small so that the parameters don't vary too much. So H parameters, the HI, HF, HR and HO, the values are fixed, they are constant. Now, later on we will see that in fact they do change if the signal changes are big. And also another important thing is, for H parameter values for a transistor, audio frequencies that is less than 20 kilohertz or something, these values are real valued. In general, they don't have to be real valued, they can be complex valued. In other words, for example, the input impedance can be not purely resistive, it could have capacitive effects also. But in this case, we do not have to worry about it. Under small frequencies, it will actually be real valued. Okay, so transistor hybrid model, we call this the transistor hybrid model, which let's look at the common emitter case, because that is what we have been working with. So this looks like this. This is my output VCE. This is my output current, simple IC, input current IB, and input voltage VBE. All simple terms. I am using the base collector and emitter. Okay, this is the active linear two-port device, so you can represent this as a active linear two-port device. So here are some notes. So the only small signal but not the operating point is found by small signal model. So parameters of the small signal model are assumed fixed within small variation of such signals, and H parameters for a BJT for audio frequencies are real valued. Okay, so with this setup, let's try to find or we try to derive the H parameters in terms of IC and IB characteristics. So let's find those values. Okay, so derivation of H parameter for a transistor in common emitter configuration. Okay, so let the dependent variables VB, so this is VB and IC are the dependent variables, right? Remember, these are AC plus DC are functions of input current and output voltage. So VB is a function of input current, simple IB. So let me say this is VBE, IB, and output voltage VCE. Okay, so this is a function of that, and this is a function of IC is a function of also IB and VCE. Right. Now, this includes simple IB and simple VCE includes. So IB is equal to IBQ plus simple I. Similarly, VCE is equal to VCEQ plus VCE. So this part is the DC component and this part is the time varying or the small signal. Okay, so DC plus AC. Okay, so now when you have something like this, if you let me remind you, if you use Taylor series expansion, okay, this is a side note. If you take the Taylor series expansion of a function around x naught, let's say my signal is x naught plus delta x, from Taylor series expansion I can write this to be equal to fx naught plus delta x times df over dx at x equals to x naught plus delta x squared d squared f over dx squared dx squared at x equals to x naught plus other higher order terms, right? So we can, this is for a single variable, so what you have is a similar setup here. So here it is like f ib and vce. Okay, so this is, let's say, 1, and this is like f2 another function ib vce. Okay, so this is like two variables, both are operating around their respective operating point, right? So therefore it is like when you have, we can generalize this like when you have two variables operating around x naught y naught, x naught plus delta x, y naught plus delta y, this expression can also be written similar to what we have written here as f x naught y naught. So this is the function value at this particular q point or the operating point plus delta x dabba f over dabba x at x equals x naught, y equals to y naught, that is basically at operating point, plus delta y dabba f over dabba y, x equals at the operating point x naught, y equals to y naught, plus some higher order terms similar to the previous one. Now here I have only written the first order terms. These two are only the first order terms corresponding to this term, and there will be similar to this second order term, there will be some second order terms also, but I'm going to assume when delta x is very small and delta y is very small, this I can approximate, this function value of this function can be approximated just to this expression here. Okay, this just these values. So this is your Taylor, this is from the Taylor series expansion where dabba f over dabba x is basically partial differential of with respect to x and y. Dabba f over dabba x is f partial differential with respect to x, and dabba f over dabba y is partial differential of f with respect to y. Okay, so if I am using this, I can write this as Taylor series expansion around the q point. In other words, IBQ VCE Q, because this I am using because IB and VCE are the independent variables, so that is why I am using those two, because that's what you have in this expression. Okay, so I can use this to derive from the first expression delta VB is equal to, so delta VB, which is equal to VBE minus VBQ, so only the time varying part. Okay, this is equal to VBE, which can be written as, from this expression, this is like the VBE part. Okay, so I can write this as WVB over WIB when VCE at the operating point times delta IB. So this is like this term. So delta IB kind of like is delta X. This is at your operating point VCEQ. Operating point VCEQ at that point. And this is my gradient. Plus I have WVB over WVC at VCEQ IBQ. So basically here also the same at the operating point. This is around the operating point. Okay, so like that, ignoring the higher order terms of the Taylor series expansion. What is this? This is equal to simple IB, and this is equal to VCE. Okay, so therefore that's my first expression. I can write it as VB is equal to WVB over I think I have WVB over WIB at VCEQ times simple IB plus WVB over WVCE at IBQ times VCE. So this is a first expression. Similarly, I can write an expression for the second equation, that is for IC. Delta IC, which is equal to IC minus IC at quiescent point. Okay, which is equal to simple IC. That is equal to WIC over WIB at VCEQ times delta IB. Let me directly write simple IB because we know what it is, plus WIC over WVCE at IBQ times VCE. So this is my second expression. So why do we have this? Because in this expression these are constants, right? So these are constants. So this is like VCE equals VCEQ and IB equals IBQ. That's kind of like what you have there. Therefore we can write, if you notice that if you take this part out, okay, and this part out, similarly if you take this out, what you have is basically the same equation as before. This is my input current, this is my output voltage. So this is like I1 V2. Okay, so therefore I can write this as VB is equal to something times IB, that something is this, okay, plus another something times VCE, but this is basically H, F and HR. Okay, you remember that? Sorry, HI and HR that you had in your expression in the previous equation. So therefore, because it is a common emitter expression, then I'm going to write second subscript as this, because these are the same equations, right? So if you compare 1 and 3, you know this comes from small signal active linear, this comes from active linear two-port theory. So therefore what you have inside this expression has to be my HIE, and whatever is there has to be my HRE. Similarly, I can, let me write it in the next page. So it's VB equals HIE IB plus HRE VCE, and IC is equal to HFE IB plus HOE VCE. Okay, so from this, by comparing these two equations to equations number 1 and 2 here, we know this should be HIE, this should be HRE, this should be HFE, and this should be HOE. Okay, so therefore I can write HIE has to be double VBE over double IB at VCE is equal to VCEQ. In other words, in the operating point. HRE has to be equal to double VBE over double VCE at IB equals IBQ. And from the second equation, we can write HFE has to be equal to double IC over double IB at VCE equal to VCEQ, and HOE is equal to double IC divided by double VCE, then IB is equal to IBQ. So at operating point, these quantities, right? And so we can draw the small signal model or the 2 H parameter model like this. So this is my IB, this is my VBE, this is my VCE, and this is my IC. Simple, all simple. This is my base, this is my emitter, and this is my collector. And this is HRE times VCE, this one, this quantity. Okay, this is HIE, this current is HFE times IB, that is this quantity, input current, times HFE, and this is 1 over HOE as a resistor. So conductance value is HOE, so the resistance is 1 over HOE, right? This is for a common emitter amplifier, right? So it's only for the common emitter, but you can generalize this to other two also. For similarly for common collector configuration, the diagram would look the same. You'll have a resistor there, something like that, current source, and another resistor there. But in this case, my input is base, just like before. Output though is my emitter, and this is my collector. So therefore, input is IB, and this is my VBC, and this is my IE, not IC, and this is VEC, and this is HIC because it's a common collector. This is HRC times VEC. This is HFC times IB. This is 1 over HOC, right? So the second subscript stands for the configuration, so for common configuration. So similarly, you can do the same for common base. You can actually find the derivation of the above expression, so these expressions using Taylor series expansion, in the textbook by Millman and Halkias, Integrated Electronics, section 8.3, page 239 to 243.